For the past decade, PCI technology has served as a ubiquitous I/O interconnect solution for computing platforms. First introduced in 1992, PCI is based on a parallel bus model with initial connectivity of 32 parallel signals operating at 33 MHz. In order to scale performance with computing requirements, the industry has either increased the number of signals or increased the signal frequency. After a decade of improvements, however, the parallel PCI model is reaching its limits, making further performance enhancements expensive, less reliable, and more complex while restricting design flexibility in delivering PCI connectivity. Here we see the effects of signal skew versus clocking due to increased frequency. Increasing the number of signals further exacerbates clocking issues by augmenting the number of signals that must be synchronized with the common clock. A new alternative for I/O connectivity is required. PCI Express technology has been developed by the industry to address the needs for the next decade's computing and communications I/O requirements. Based on a serial model, clocking data at 2.5 GHz via two differentially signaled half-duplex lane pairs of wire, PCI Express technology addresses the fundamental issue of performance scaling by encoding clock and data into a single stream utilizing SerDes silicon. As a result, we are able to increase signaling speed significantly while dramatically reducing the number of signals. The resulting reduction in pin count increases design flexibility while creating more efficient and cost-effective I/O solutions. PCI Express technology was designed to utilize the extensive industry investment in software development by featuring backward software compatibility with legacy PCI infrastructure. PCI Express architecture will be used in a wide range of design platforms as a chip-to-chip and chip-to-adapter technology. Desktop and notebook designs will utilize PCI Express slots and connectors, along with Express card modules to deliver efficient connectivity solutions and true plug-and-play capability. These benefits are offered while simultaneously enabling an enhanced graphics performance roadmap and the transition to Gigabit Ethernet. By scaling the number or width of links, PCI Express technology can scale performance to enterprise requirements. The PCI Express specification enables multiple link widths, or presumably up to 80 gigabits per second of link performance at a 2.5 gigabit per second signaling rate, and can be further enhanced through signaling rate increases. Scaling width and frequency within a serial infrastructure does not have the same limitations as discussed in a parallel model due to each signal containing encoded clock and data. Servers are expected to utilize PCI Express technology via slots, server modules, and motherboard implementations. Next-generation modules and motherboard configurations deliver new flexibility in server motherboard design, aiding in delivery of dense rack mount and blade servers. By matching the performance requirements of 10 gigabit per second interconnects, PCI Express technology enables balanced server platforms, freeing processing power from traditional I/O bottlenecks. PCI Express technology also extends PCI's role in the communications industry. Within an internet infrastructure, PCI Express technology will be found embedded in traditional communications applications as well as extended into new interconnect uses. Initial PCI Express implementations will transition PCI-based connections to the higher performance and lower pin count offered by PCI Express designs. The industry is moving forward to PCI Express solution delivery.
Do you remember when you first realized that your computer was more than just a monitor and keyboard? That between the mouse click and the video playing, there was something that captured your attention, understood it, and made it real? What is that something? Is it gremlins? Let's imagine that we can shrink down to the size of an electron and inject ourselves into a click of a mouse. If you took your mouse apart, you'd see that it's really a very simple machine. It has a couple buttons and a system for detecting motion and distance. You might have an optical mouse that makes these measurements with lights and sensors, but older ones did this with a hard rubber ball and some plastic wheels. Same concept. When you click the button on your mouse, it sends a message to the computer with information about its position. When your mouse click is received, it's handled by the basic input-output subsystem. This subsystem acts like the eyes and ears and mouth and hands of the computer. Basically, it provides a way for the computer to interact with its environment. But it also acts like a buffer to keep the CPU from being overwhelmed by distractions. In this case, the I/O subsystem decides that your mouse click is pretty important, so it generates an interrupt to the CPU. Hey CPU, got a click here. The CPU, or Central Processing Unit, is the brains of the whole computer. Just like your brain doesn't take up your whole body, the CPU doesn't take up the whole computer, but it runs the show all the same. And the CPU's job, its whole job, is fetching instructions from memory and executing them. So while you're typing, maybe really fast, like 60 words a minute, the CPU is fetching and executing billions of instructions a second. Yes, billions, every second. Instructions to move your mouse around on the screen, to run that clock widget on your desktop, play your internet radio, manage the files you're editing on the hard drive, and much, much more. Your computer's CPU is one heck of a multitasker. But oh my gosh, there's a very important mouse click coming through now. Let's drop everything now and deal with that. There are programs for everything that the CPU does. A special program for the mouse, for the clock widget, for the internet radio, and for dealing with letters sent by the keyboard. Each program was initially written by a human in a human-readable programming language like Java, C++, or Python. But human programs take up a lot of space and contain a lot of unnecessary information to a computer, so they're compiled and made smaller and stored in bits of ones and zeros in memory. The CPU realizes that it needs instructions for how to deal with this mouse click, so it looks up the address for the mouse program and sends a request to the memory subsystem for instructions stored there. Each instruction in the mouse device driver is duly fetched and executed. And that's not nearly the end of the story. Because the CPU learns that the mouse was clicked when the cursor was over a picture of a button on the monitor screen, and so the CPU asks memory for the monitor program to find out what that button is. And then the CPU has to ask memory for the program for the button, which means that the CPU needs the monitor program again to show the video associated with the button, and so it goes. And let's just say that there are a lot of programs involved before you even see the button on the screen light up when you clicked it. So just the simple task of clicking your mouse means visiting all of the critical components of your computer's architecture. Peripherals, the basic input-output system, the CPU, programs, and memory, and not one gremlin.
Inside every computer is a central processing unit, and inside every CPU are small components that carry out all the instructions for every program you run. These components include AND gates, which only allow electricity to flow to their output wire if all their input wires are on. The AND gates use tiny transistors to control the flow of electricity to the output wire. The electricity from another part of the computer flows in from the top and gets stopped at the first transistor unless its input wire is on. When that input wire turns on, it causes an electric field to form around a small piece of insulated metal. This electric field reaches out past the insulation and causes the properties of the semiconductor material below it to change, turning a small part of that semiconductor into a full conductor, bridging the gap for any electricity flowing in from the left and out to the right. The types of components you create from transistors are based upon how you wire their inputs and outputs together. If you chain them together so that the output of one flows to the input of the next, then you are creating an AND gate, where all the input wires must be on for the final output wire to be on. Inside the Scott CPU, you'll see a number of these AND gates scattered around, with some having more inputs than others. Another type of component that you'll come across is the OR gate, which is represented by this shape. Instead of chaining the output of each transistor to the input of the next, you instead run all the output wires to the same place, the output of the whole gate. In this way, if any of the transistors have their input wire on, then electricity flows straight through them to the gate's output. You'll also see a number of these OR gates scattered around the Scott CPU. By the way, the Scott CPU comes from the book But How Do It Know by John Scott, which is available at his website, buthowdoitknow.com. It includes a great explanation of how computers work for beginners, and John was kind enough to allow his CPU design to be used in this video. The other basic component you'll see in any CPU, including the Scott CPU, is the NOT gate. The NOT gate uses a transistor to divert the electricity already flowing to the output of the gate to a ground wire, effectively short-circuiting the output wire, turning the output of the gate off if the input wire is on. There are a number of these NOT gates inside the Scott CPU, not only in the locations seen here, but also inside the other components. For instance, the stepper component is just a particular combination of AND, OR, and NOT gates, where the output wires turn on in sequence each time the input wire to the stepper turns on. This input wire comes from another small component called the clock, where the output wires turn on and off again very quickly in a steady pattern. The only other component used in this part of the CPU is the selector, formed from another combination of AND, OR, and NOT gates that turn on one of several output wires depending upon what input wires are on at the moment. In another area of the CPU is the arithmetic logic unit, which includes more AND, OR, and NOT gates, along with the selector component that we just saw. There are a few other components in the ALU, like the exclusive OR and the NOR gate, but these are just made from the same OR gates we saw earlier, along with some AND and NOT gates. In other videos, we'll see how these components work together to process instructions sent to the CPU. This has been a brief look at what's inside the CPU.
RAM and ROM. All computer storage falls into two broad categories: primary storage and secondary storage. Primary storage can be further split into two main types: RAM and ROM. RAM is a fast temporary type of main memory. It is used to store data and programs the computer is currently using. It is much quicker to access information stored in the RAM than it is off a computer's hard drive or another secondary storage device, such as a DVD or USB pen. Typically, at any moment in time, RAM will hold three things. It will hold the operating system, or the part of the operating system currently in use. It will hold any programs that the computer is currently running, and it will hold any data that those programs are accessing. For example, if you're watching a movie called movie.mp4, RAM would contain the parts of the operating system which are responsible for processing sound and audio. The program which was actually playing the movie would also be in RAM, such as Windows Media Player or iTunes. And the actual data that Windows Media Player or iTunes was using, in this case the file movie.mp4. RAM is volatile, which means that when the power is turned off, it will lose all of its contents. In order to keep the information which is stored in RAM, it must be written back to a permanent storage device, such as the computer's hard drive. The other type of primary memory is ROM, or read-only memory. ROM is a type of memory which cannot be changed by a program or the user. ROM's main difference from RAM is that it is non-volatile in nature, so it retains the information held in it after the computer's been switched off. ROM chips are typically found actually embedded onto the motherboard of a computer, and they're used to hold important instructions which the computer needs for starting up. To summarise, here are the main differences between RAM and ROM.